Welcome back to the Chem OG. Today we're going to take a look at some strategy as it relates to biochemistry. And in particular, we're going to take a look at the isoelectric point. And so the isoelectric point is a particular pH, and it's the pH that allows our amino acid or our peptide chain, because sometimes we're looking up a whole bunch of amino acids together. It's the pH at which our amino acid or our peptide chain is neutral in terms of its charge. And a lot of times that form of the molecule is called your Zwitter ion. And it's called a Zwitter ion because you have a charge separation, but it's overall neutral, coming from the German word for Zwitter, meaning that you have a duality going on. You got two things that are at odds with each other, a plus charge and a minus charge. And so where does the charge on an amino acid come from? Because if we understand where the charge is coming from, we can understand how it is that we can make our overall molecule neutral. So let's take a look at that. So let's talk about the functional groups that can give a positive charge to our amino acid. So positive charge is either going to come from the N-terminus at certain pHs, or it's going to come from amino acids that have basic R groups. And if you want to remember the basic and the acidic R groups together, think of the gambler Hercules. Like if you think of the Greek legend Hercules and you think of him as a gambler, HRK together, they kind of spell out Hercules in a weird way, H, R, and K. So histidine, arginine, and lysine are amino acids with basic R groups. So for example, if I take a look at arginine, arginine's R group has a nitrogen that carries a positive charge. Okay, and you'll also notice that the N-terminus, right? If I take a look at my alpha amino group, it's also possible that it can carry a positive charge as well. So in terms of positive charges, it can be carried by the N-terminus or by the R group of certain amino acids, and in particular, those that are histidine, arginine, and lysine. If we also take a look at the structure of lysine, we'll notice that the nitrogen here on the R group also carries a positive charge. So the positive charge is either going to be carried by the N-terminus itself, right? And it can also be carried by the R groups of histidine, arginine, and lysine. What about the negative charge? Well, the negative charge is going to come from a variety of sources, and in particular, it's going to come from the C-terminus. Carboxyl terminus, when it gets deprotonated, becomes a carboxylate, so that's a source of negative charge. Another source of negative charge is amino acids with acidic R groups instead. And you can remember the four of them by remembering the mnemonic dice. So remember when I told you Hercules was a gambler? Well, Hercules always has a pair of dice on him at all times, just in case. Just for emergencies. And so DYCE, D, remember, is the one-letter abbreviation for aspartic acid, Y is the one-letter abbreviation for tyrosine, C, cysteine, and E is for glutamic acid. So those are the molecules whose R groups, or those are the amino acids whose R groups are capable of producing a negative charge at certain pH points. So for example, if I take a look at tyrosine, tyrosine has a phenol group, and that phenol group at certain pHs can possess a negative charge. And you'll also notice that the carboxyl group, right, the C-terminus, can produce a negative charge at certain pH points. And if you're wondering when those pH points are, because I keep saying that, it's like at certain pH points this could happen, when exactly does that happen? We'll take a look at the particular property of an amino acid that allows us to be able to determine whether that proton is there or whether that proton is not. Other structures, just to kind of give you an idea, is if we take a look at the R group for cysteine, when cysteine becomes deprotonated, its sulfur group, its thiol, becomes a thiolate and can carry a negative charge. If I take a look at the structure for, in this case, it's aspartic acid. Aspartic acid, when it gets deprotonated, becomes aspartate. And so I'll have a negative charge here instead of its normal neutral self. So now that we learned that positive charge comes from the nitrogen-containing R groups, histidine, arginine, and lysine, and it also comes from the N-terminus, and now that we learned the negative charge comes from dice and the C-terminus, how does that help? Well, the way that we know whether a functional group has a proton attached or doesn't, it's by taking a look and comparing the current pH to the pKa value. And each functional group has a unique pKa value. And so what you can do is you can look up the pKa value for a particular R group on an amino acid, or the C-terminus or the N-terminus. And it would look, and that table would look like this. So here we have the full name of each of the 20 amino acids. And then, in this column, we have the 3-letter abbreviation for that amino acid. Here's the 1-letter abbreviation for that amino acid. And you'll notice that each of the amino acids has a pKa1 value and a pKa2 value. The pKa1 value is the one for the C-terminus. It's the lower of the two values because the C-terminus is more acidic. And then the pKa2 value is the N-terminus, and that value is higher because the ammonium group is not as acidic as the carboxyl group on each of our amino acids. And then you'll notice that there are certain amino acids that also have a pKar value in this column. Okay, and notice that the dice amino acids, DYCE, those are the ones that are here, right? And these are the ones that belong to acidic R groups. And you'll notice that the histidine, arginine, and lysine values, those I have here in blue, those belong to basic groups instead. Or really, technically, it's the pKa of the conjugate acid of those groups. Okay. Now, you might notice that the values here are a little bit erratic. Like, if you're looking at the R group for an acidic side chain, you would expect that all of them would be below 7. But notice that, for example, tyrosines is actually above 7. Same thing for cysteine. Like, why are those above 7? Well, the idea is that even though they're not as acidic as, say, glutamic acid or aspartic acid, when they do donate a proton, as you guys saw, they give us a negative charge. So that's why we're clumping them all together. And with histidine and lysine and arginine, when those guys, have their proton attached, they all have a positive charge instead. And so that's the reason for clumping them together. It's not that their acidities are, completely comparable. They're not. It's just when we say that we have an acidic R group, it means that when it's protonated, it's neutral, but when it gives up its proton, it's negatively charged, as you guys saw. And then for the basic R groups, they're the ones that when they're protonated have a positive charge instead. And so to determine the isoelectric point for a peptide chain, in other words, a whole bunch of amino acids added up together, the first thing you should do is be able to determine the maximum possible charge. And so what's the maximum possible charge? It's when everything is as positive as possible. And the only things that give us positive charge are the N-terminus and Hercules, H, R, and K. So I'm adding a 1 here because every single peptide chain has an N-terminus. So the 1 here is added for the N-terminus, and then depending on how many histidines, arginines, and lysines you have, those are going to carry a positive charge as well. So the maximum charge on our entire peptide chain is found by counting the number of instances of histidine, arginine, and lysine, and then adding 1 to account for the N-terminus. Okay, so the reason that I want to determine my maximum possible charge is that it gives me an idea of how many protons I need to remove in order to become neutral. So for example, let's say that my maximum possible charge is a +5. Well, in order to become neutral, I would need to remove 5 protons from that peptide chain to get me back to 0. So when we say neutral, it means that we need to have a 0 charge. But each of these histidines and arginines and lysines and the N-terminus is something that provides positive charge instead. So by determining the maximum possible charge, I can figure out how many protons I need to remove in order to get me back to neutral. And so the next step we want to do is we want to list out all the pKa values from least to greatest, so in ascending order. And once we have that list of pKa values, all you need to do in order to determine your isoelectric point is find the average of the nth number, and remember n is your maximum possible charge, and of the number that follows it. So if our maximum possible charge is 5, take a look at all of your pKa values, find the 5th value, and take a look at the value that's after it, or in other words, the 6th value, and then average those two numbers to get your isoelectric point. So sounds complicated until you start doing it. So let's try it. So what about this octapeptide? Vahelink, if I'm pronouncing it phonetically, right? You got 8 amino acids that are linked up together in a peptide chain, and you're trying to figure out the isoelectric point of the entire thing, okay? Which is certainly more complicated than trying to figure out the isoelectric point of a single amino acid. So here's what we're going to do. Here's our octapeptide over here. And so the maximum possible charge on this entire peptide chain is 3. And the way that I know that is the N-terminus over here is going to have possibly a plus charge, depending on pH. And then let's count up how many histidines, arginines, and lysines we have, how many Herculeses we have. So I have an histidine, and I also have a lysine over here. And those are the only two that can give me a positive charge in addition to the N-terminus. So my maximum possible charge is 3. Now, the next thing I'm going to do is I'm going to take a look at that table of values again. Okay, in order to determine what's going on with my pKa1s and my pKa2s and any R values that I need to be able to incorporate as well. Because after I figure out my maximum possible charge, I need to figure out all my relevant pKa values. And so I'm going to start off with the N-terminus here. The amino acid at the N-terminus is valine. Remember that we always read our peptide chains from N to C, from N-terminus to C-terminus. And so valine here is the one that's at my N-terminus. And so I need to find out the pKa of the N-terminus of valine. So here's valine right here. The pKa value of the N-terminus of valine, remember you're looking at pKa2s, is 9.62 according to this chart. Okay. Now let's take a look at the C-terminus. At the C-terminus I have lysine. So what I need to do is I need to find lysine's entry over here, and I need to find the C-terminus value for lysine. So that is going to be 2.18. Okay, what else do I need to do? Well, any amino acids that have a value in the pKa-R column are ones I need to list out as well. And so glutamic acid is on that list, histidine's on that list, tyrosine's on that list, and lysines on that list. So let's write out their pKa values. I'm going to start out with glutamic acid. So for glutamic acid, the R group value is 4.25. So I'm going to write that down. Next one is histidine. That's going to be a 6. Next one is tyrosine. That's 10.07. And the one after that is lysine, and that is 10.53. So here are all our pKa values all put together. And in total, we have 6. Okay, and what that means is there are 6 possible functional groups that can donate the protons on this molecule. Now, how does that help me exactly? Well, remember, the maximum possible charge tells you how many protons you need to remove. And so I'm going to list out my pKa values in order, right? So that's going to be 2.18 because the lowest value is for the C-terminus, and then 4.25, 6, 9.62, 10.07, 10.53. And the isoelectric point is going to be the average of the third term and the fourth term. Why? Because our maximum possible charge is 3. And so I'm going to start taking a look at my third term in that ordered pKa value list, and I'm going to average it out with the fourth term. So 6 and 9.62 divided by 2. When you want to find the average of two numbers, you add them up and divide by 2. So that's going to give me a number that is slightly, a little bit less than 16. If 9.62 is right around 10, 6 plus 10 is 16 divided by 2. I'm going to get a number that's less than 8. And in fact, the isoelectric point of this amino acid is 7.81. So whichever two values you end up averaging are not consistent. It depends on what the functional groups are and which amino acids you're looking at in particular, but it is always going to be whatever your maximum charge is, and then the one after that too. Now, if you're still wondering why it is that we're taking a look at the third and the fourth term, or why it is that we take a look at the maximum charge and what number that tells us, and then the term after that. All right, so let's take a closer look at what we got going on with those pKa values. So here's our octapeptide again. And when my pH is really, really low, that's when I have my maximum possible charge. So when everything is protonated, I'm going to have a +3 because all my histidines and arginines and lysines and the N-terminus are all going to be protonated. They're going to contribute a plus charge. Now, at each new pKa point, what happens is I lose one proton. And at the next pKa point, I lose the next most acidic proton. At the next pKa point, I lose the next most acidic proton. And so what I did here was I put a whole bunch of arrows. And on top of those arrows, I put down the pKa values that we saw from before, from lowest to highest. And that's because the lowest pKa value represents your most acidic acid. So that's the one that's going to lose its proton first. And so when I was at my +3 state, I'm going to start losing my first proton when I get to pHs higher than 2.18. I'm going to lose my next proton at the next pKa value and the next proton at the next pKa value. So check out how many deprotonations had to happen in order for me to reach 0. So I needed 1, 2, 3 deprotonations in order to reach 0. And in order to go to -1, I would have to go through a fourth deprotonation. And so if I want to make sure that as much as possible my molecules have a 0 charge, I'm going to look for the average of these two pK values. I don't want to be close to 6, and I don't want to be close to 9.62. I want to be sort of nestled in between here, so that way I'm far away from these two as I can be. And so your maximum possible charge tells you how many deprotonations you have to go through. And incidentally, this is actually a great little way for us to be able to tell the overall charge on the octapeptide at any pH point whatsoever. Because now, if you give me a pH value, I can tell you exactly what the charge on the molecule, which charge on the molecule is going to dominate. So for example, let's say that I'm asking for the charge on the molecule at physiological conditions. Well, physiological conditions are a little bit, above 7 in terms of pH, and 7 is right between 6 and 9.62. So I actually expect this octapeptide to be neutral at physiological conditions. Let's say we take another value of, say, 3. So a pH of 3 is somewhere between these two values over here. So I expect that my molecule is going to have a +2 charge. Let's say we take a pH value of 13. Well, 13 is above 10.53, and so I expect that my molecule is going to have an overall -3 charge. And if you're wondering where that -3 charge might come from, well, it's going to come from the fact that the C-terminus itself is negatively charged. We also have a tyrosine that's going to be negatively charged at that point, and we have a glutamic acid that's going to also be charged as well. And so writing out all of your charges and all of your pK values on arrows like we did, and then doing successive deprotonations is a really insightful way of being able to tell what the charge is on your peptide chain at any old pH point. So in summary, what you want to do is you want to find the maximum possible charge, and you're going to get that from histidines, arginines, and lysines, and add 1 to those to account for the N-terminus. List the pK values in order, including the value for both the C and the N-terminus, and then your isoelectric point is going to be the average of the nth pKa. So depending on your charge, right, find that value, and then the one after that in the list, take those two numbers and average them out. Thank you so much for watching today's video. Please be sure to hit the like button, and if you haven't done so yet, please make sure to subscribe to support this channel. See you at the next video.